In the last class we discussed all the basics about the metals, physiological action, you can just draw again porphyrin. First I will draw porphyrin. Porphyrin is without substitutions. Altogether 24 numbering. Two different diagrams I have drawn. In the first one I have just labeled the numbers. In the next it is positions. So what do you call these positions as? Altogether how many alpha, how many beta positions? You can see altogether there will be 8 alpha positions, 8 beta, 4 meso positions. Meso positions are the connecting links between the pyrrole rings. From the second structure we can show porphyrin also. In the second we can also show the porphyrin. Suppose if I continue with the porphyrin, COO minus this is porphyrin. Without any substitutions I simply call it as porphyrin. With substitutions I call it as porphyrin. So where are the substitutions? All substitutions are at beta positions. Alpha position, there is no possibility for any substitution. Meso, there are no substitutions. Synthetically, we can prepare some porphyrins where meso positions can also be substituted. But naturally available porphyrins, they do not have any substitutions at meso positions. Only beta positions will be occupied. That too, it will be occupied only by alkyl groups. No aromatic groups will be there at beta positions naturally. You have to remember that point. Completed diagram? Okay, first I'll explain, then I'll give you the points. Yeah. First you listen and then I'll give you the points. So here we are starting with a porphyrin. Porphyrin is made up of 4 pyrrole rings. 4 pyrrole rings which are 5-membered rings. These 5-membered rings are connected with methane bridges. We simply call it as a methane bridge, a CH bridge. So 1 CH, second, third and fourth. Altogether there will be 11 double bonds and all these double bonds will be in conjugation. So 11 double bonds will make 22 pi electrons. Is it following 4n plus 2 Huckel's rule? 4n plus 2 pi electron. 4 into 5 plus 2 will be 22. So it is following 4n plus 2 Huckel's rule. Hence we call porphyrin or porphyrin to be aromatic. We can call it as a aromatic macrocycle. Okay? It is an aromatic macrocycle. Next point. We have 4 nitrogens. Of these 4 nitrogens, the lone pairs of 2 nitrogens can also participate in conjugation. So with 2 pairs of lone pairs, altogether 22 plus 4 electrons, it is also called as a 22 electron system. It is also called as 26 electron system. 22 electrons coming from pi bonds. 4 electrons coming from 2 lone pairs of 2 nitrogens. Which nitrogens contribute, we cannot say. The reason is, whatever hydrogens that you are seeing here, 1 on 21 and 1 on 23, these 2 hydrogens will not remain at their position. They keep on jumping. These hydrogens, they keep on jumping. They keep on shifting. So this hydrogen from 21, it will shift to 22. This will shift to 24. So shifting is continuous. The 2 hydrogens are not found to be static. They are found to be dynamic. They keep on shifting. In this shifting, we will be getting 2 different tautomers. One we call it as 21-22, which is called as a cis tautomer. The another one is 21-23, which is called as a trans tautomer. Cis as well as trans. Between these 2, trans was found to be more stable. Okay? So between cis tautomer and trans tautomer, trans is found to be more stable. Cis we call it as 21-22, least numbering. I need not say 23-24, we can just say 21-22. Trans 21-23, you need not say 22 and 24. Okay? So all these double bonds are in conjugation. 2 lone pairs can also participate in conjugation. So I can call it as a 22 electron system or it is a 26 electron system. So whether it is aromatic or not, even NMR gives us some data. Whichever hydrogens are outside, those hydrogens, they are found to be downfield. They resonate downfield. And whatever hydrogens are present inside, these are found to be upfield. So even NMR data says that it is aromatic, and according to your organic chemistry, it resembles 18-annuline. Porphyrin or porphyrin, it resembles 18-annuline. Okay? So even in the NMR spectra, the inside protons will resonate upfield, outside protons will resonate downfield. Right? Next. Suppose if I'll just show it here. If I add 2 hydrogens, what will happen? 2 nitrogens are present, I am adding 2 hydrogens. If at all I add 2 hydrogens, there will be a positive charge. There will be a positive charge over nitrogen. So whenever I add 2 hydrogens, we call it as a dication, porphyrin dication. It means porphyrin can act as a base. As a base it is taking protons. Once it is taking protons, two positive charges are coming, and due to these two positive charges it can act as a dication. Okay, so it is acting as a base taking protons. That is one way. It can also act as acid. Protons will be given away. Once protons are given away, what will be the charge? H plus is gone. So you have two minus charges. With these two minus charges, it can behave as dianion. It can act as a weak base. It can also act as a weak acid. It can behave as a dication. It can behave as a dianion. But the most commonly found in is dianion. You find porphyrin or porphyrin mostly to be dianionic form. That is the reason whenever you write chlorophyll, what is the oxidation state of magnesium? +2. Because it is a dianion, this will get 2 positive charge. Or I take iron, 2 positive. First of all, we start with deoxy hemoglobin. Iron will be in +2, magnesium +2. So most of these will be in +2, and this will act as a dianion. So mostly porphyrin or porphine will act as a dianion. Okay, it can act as a dication, it can act as a dianion. Dianion is the most common, right? So you just note down all these points regarding the porphine or porphyrin. Which position is this? Beta, but numbering? Third. At third position, suppose if I am replacing this group by a CHO group, I am just replacing that group with a CHO group. Does it make any changes within the pigment? Does it change any chemistry, or does it give any changes? Suppose if this is a porphyrin, okay, in that porphyrin at third position, simply instead of a double bond, I am changing it by a CHO. Just an oxygen is being added. That brings a lot of changes. Lot of changes will come. That pigment is called as chlorochlorine. The pigment is completely changing. We call it as chlorochlorine. You might have heard about annelids, earthworms, etc. So in annelids, it has a pigment, just as we have hemoglobin, that will have chlorochlorine. And what is the difference? Only difference is at position 3, instead of a double bond, it has a CHO. And what is the color of porphyrin? Purple. It is purple color. But this chlorochlorine, just one bond we are changing, and the color completely changes to green. Chlorochlorine will be green in color. And light red. So why did I write two colors? There are two colors. The reason is chlorochlorine is called as a dichromatic compound. Dichromatic compound means it can exhibit two different colors at different dilutions. At very high dilution, it will exhibit green color. At very low dilution or at a greater concentration, it can exhibit light red color. So depending on the concentration or the dilution, colors will change. More dilution, green color. Lesser dilution or more concentration, red color. Chlorochlorine therefore is called as a dichromatic compound. Dichroma. Chroma is related to color. Di is twice. 2. So it can exhibit two different colors. And you are getting that chlorochlorine by changing just one position at third. Okay. So first note down the points about this. Porphyrin has 8 alpha positions, 8 beta positions, and 4 meso positions. And 4 meso positions. Next, alpha positions cannot be substituted. Alpha positions cannot be substituted. Next, naturally available porphyrins. Naturally available porphyrins contain beta octa alkyl substitutions. Naturally available porphyrin contains beta octa alkyl substitutions. Beta octa alkyl substitutions. Example, porphyrin. Example, porphyrin. Porphyrin is a porphyrin with 8 octa alkyl substitutions. Octa is 8 alkyl substitutions. You can see the positions also. Next, naturally available porphyrins. Naturally available porphyrins. Naturally available porphyrins do not contain aryl substitutions. Do not contain aryl substitutions. But synthetically prepared one can have aryl substitutions. Can have aryl substitutions. That is meso tetra aryl substitutions. Meso tetra aryl substitutions. Meso tetra aryl substitutions. Next, 11 double bonds are in conjugation. 11 double bonds are in conjugation, making it 22 electrons. Making it 22 electrons, comma, aromatic. Next, two lone pairs of nitrogens. Two lone pairs of nitrogens also participate in conjugation. Two lone pairs of nitrogens also participate in conjugation. This makes 26 electrons. This makes 26 electrons. Next, the outer protons resonate upfield in NMR. The outer protons resonate upfield in NMR. Outer protons resonate downfield. Outer protons resonate downfield in NMR, whereas inner protons resonate upfield. Inner protons resonate upfield. Next, porphyrin resembles 18 annulin. Porphyrin resembles 18 annulin. Next, 21H 23H tautomer is more stable. (21H 23H tautomer is more stable than 21H 22H tautomer. 21H 23H tautomer is more stable than 21H 22H tautomer. 21, 23 is trans. This is cis. Next. The two hydrogens on nitrogen, are dynamic. The two hydrogens on nitrogens are dynamic. Dynamic means they keep moving over all the four nitrogens. They keep jumping over all the nitrogens. They keep jumping over all the nitrogens. They keep jumping over all the nitrogens. Next point. Porphyrin can act as a dication. Porphyrin can act as a dication. In bracket, weak base or close the bracket, or a dianion weak acid. Porphyrin can act as a weak base and a weak acid, dication and dianion. Next, naturally available porphyrins mostly act as dianions. Next, at third position of porphyrin, when CHO is substituted, it behaves as another pigment. Called chlorochlorine. It is a dichromatic compound. Found in annelids. It exhibits green color. It shows green color at dilution. And light red color. It shows green color at dilution and light red color at concentration. Okay, so these are some points about porphyrin and porphyrin. Next point, you just write down. Porphyrin is found in oxygen binding protein. Example, hemoglobin. Okay, so now we will just start with oxygen binding proteins. Today we will begin with hemoglobin. What are the different oxygen binding proteins? You may write down. Hemoglobin, we also abbreviate it as HB. HAEMO or HEMO, they are one and the same. In some literature you may find it as HAEMO, olden books. HEMO, both are correct. Myoglobin, it is abbreviated as MB. Hemerythrin is abbreviated as HR. Myohemerythrin, it is abbreviated as MyoHR. Last one is hemocyanin, abbreviated as HC. Capital H, small b, capital H, small c, capital M, small b, capital H, small r. Those are the abbreviations. Hemoglobin, myoglobin. Myoglobin is the monomer of hemoglobin. Hemerythrin, myohemerythrin. Myohemerythrin is the monomer. Hemocyanin has no monomer. You don't find monomer, but different subunits are there. So let us begin with hemoglobin today. Finished? Myohemerythrin, last one is hemocyanin. Hem means, what do you mean by hem? Hem is iron or metal surrounded by prosthetic group, that is called as heme. But in olden literature, according to Greek, heme means blood. Simply it was related to blood. But this is no more agreed now. Previously, heme means blood. So they named it as hemoglobin, hemerythrin, hemocyanin. So wherever they mentioned it as heme, it was related to blood. But now heme means it is not blood, it is that portion where the metal is surrounded by a prosthetic group. Prosthetic group means, suppose I am taking iron, iron is surrounded by porphyrin. This particular unit I can call it as heme. Iron surrounded by porphyrin, I call it as a heme. But I cannot call hemerythrin where metal is surrounded by some other amino acids. It is not surrounded by porphyrin. So this cannot be called as heme. Truly speaking, this cannot be called as heme. But why did they name heme? Heme is simply related to blood. That was the olden literature. But now heme is any portion where the metal atom is surrounded by a prosthetic group such as porphyrin. So hemoglobin is a heme protein. Hemerythrin is non-heme protein. It is a non-heme protein. Though name has heme, but you have to call it as a non-heme iron protein, non-heme copper protein. Okay? But why heme is mentioned? Because it was, heme means blood. Just like your chromatography. Chroma means color. But with chromatography I can separate colorless compounds also. First intention was to separate colored compounds. That is the reason they mentioned it as chromatography. But now we are even separating colorless compounds. Still we are using the same name. Similar this way. Write down a point. Heme means blood according to Greek. According to Greek, heme means blood. Heme means blood. But it is that portion, where metal is surrounded by, a prosthetic group. Metal is surrounded by a prosthetic group. On board I have written, metal is surrounded by a prosthetic group. Example, in hemoglobin, iron is surrounded by, porphyrin. Hence HB means hemoglobin. HB is a heme protein. Whereas HR means hemerythrin. HR is a non-heme iron protein. and HC is a non-heme copper protein. HC is a non-heme copper protein. Okay. In bioinorganic chemistry, every point can be a potent question. Always remember, every point can be a question. They may ask you which of the below is a non-heme iron protein. So non-heme iron protein, they may give you hemoglobin, hemerythrin, hemocyanin, myoglobin. It is non-heme iron protein. So it has to be hemerythrin. So you have to be very careful regarding each and every point. Right. So now let us move to hemoglobin. Today we will begin with hemoglobin. So before going into hemoglobin, first of all, I'll just explain a simple mechanism. Almost every one of you are from math background. Most of you are from science background. Math or science? How many science? Oh, many are science, so no bothering. But I don't know how many are science background from online. Some of them will be mathematic background. So just within 2 to 3 minutes, I'll explain the process of this hemoglobin taking up the blood. I mean, hemoglobin taking up the dioxygen. Okay? Right. First of all, we do respiration. Respiration means inhalation and exhalation. That is at normal level, at biological level. Truly speaking, respiration is a process where energy is produced. That will be done at the tissue or cellular level. But in general, whenever we say respiration, inhalation and exhalation, it is at outer level. We breathe in. And whenever I breathe in, along with nitrogen, oxygen also go. But nitrogen, does it go and bind with hemoglobin? Why not? It is almost 80% nitrogen. Only 20% is dioxygen, but only dioxygen goes and binds. Nitrogen does not bind because nitrogen is inert. Nitrogen is inert with a triple bond. It is very stable. So though we are inhaling lot of nitrogen, but nitrogen does not bind, only oxygen will bind. The reason? Oxygen is a triplet. Thermodynamically speaking, I said it is very reactive because it is a spin triplet. There are 2 unpaired electrons in it. But if I look at nitrogen, there is no unpaired electron. It is very stable. So though more amount of nitrogen I am inhaling, it is completely inert. So nitrogen does not bind with iron. It needs more activation. If at all a dinitrogen wants to bind with any metal, it requires more activation. That much activation is not there at hemoglobin level. So once I am inhaling, all that air will be entering into the lungs. Within the lungs, we have small chambers called as alveoli. Alveoli are the small pores where gases will exchange. Gases exchange means once I am inhaling, whatever oxygen that is present, that oxygen will be taken up by the blood. Blood contain hemoglobin. How much iron will be present in our body approximately? Approximately? An average human being, whenever I say an average human being, that human who weighs 70 kg of weight, they are called as an average human being. So whatever we refer to as an average human being. A human being with 70 kg will have 5 liters of blood. So whenever I say average human being, 70 kg weight man or a woman will be an average human being. Approximately we will be having 5 grams of iron within us. In our complete body we will be having 5 grams of iron. Out of this 5 grams of iron, 2.6 grams nearly is present in hemoglobin. In hemoglobin itself, half of the iron is present. The remaining iron will be present in some other ways. Ferritin and different ways it will be present. It can be stored also. Myoglobin and so on. But in hemoglobin, you will be having 2.6 grams of iron. So once I have inhaled all that oxygen, now forget about nitrogen, all that oxygen, we have a higher partial pressure in the lungs. So at that very high partial pressure, hemoglobin will come, it will bind to the dioxygen. As it binds to the dioxygen, slowly through blood it will be moving to the tissue level or the cellular level. Once I go to cellular level, the partial pressure of oxygen will be low. Because at lungs I am inhaling, partial pressure will be very high. But at tissue level or cellular level, the partial pressure of oxygen will be low. Whenever the partial pressure of oxygen is low, your protein called as hemoglobin, it cannot bind with oxygen. It is ready to give away oxygen. So that is one reason why it is giving away oxygen. Bonding is not strong, it is reversible binding. Reversible binding means weak binding. So it takes at a higher partial pressure, goes to lower partial pressure, immediately it will give away. That is first reason. Second reason, whenever acidic conditions are more, hemoglobin will lose the capability of binding dioxygen. Always remember this. At higher acidic conditions, hemoglobin will lose oxygen binding capacity. So at lungs, oxygen is more. But when I go to tissue level, what will happen? Process of respiration will occur. All the glucose will be taking up the dioxygen. It will burn the glucose, and what are the side products? Once the glucose is burnt, water will come. Carbon dioxide will also come. That carbon dioxide will dissolve in the water. That will form carbonic acid. Carbonic acid will be formed. So at tissue or cellular level, I have acidic environment because of formation of carbonic acid. Whatever carbon dioxide that is released, immediately it will be in the vicinity of the cell. It will create an acidic environment. So at that acidic environment, hemoglobin will lose oxygen binding capacity. It is getting oxygen from the lungs, going to the tissue level. At tissue level, partial pressure of oxygen is low. Also there is acidic condition. Under acidic condition, hemoglobin cannot bind dioxygen. It will give away dioxygen. Once it has given away dioxygen, whatever carbon dioxide that was mixing with water giving carbonic acid, H plus HCO3 minus, those H plus HCO3 minus will come and attach to hemoglobin at different parts of hemoglobin. It will not come directly as carbon dioxide. Carbon dioxide will mostly come as carbonic acid. 80% will be nearly carbonic acid. The remaining 20% of carbon dioxide will bind to hemoglobin at tissue or cellular level. Slowly through blood flow, again it will come to lungs. At lungs, partial pressure of oxygen is very high. So it will give away the carbon dioxide. Whatever carbonic acid is present, that will be back converted into carbon dioxide. It will be exhaled at alveoli. Again the same process will continue. So two things that you have to remember. First thing, protein can bind to dioxygen at high partial pressure and low acidic condition. Temperature should also be less. Okay. Now once I am going to a tissue level, at tissue level partial pressure of oxygen is low, therefore hemoglobin gives away oxygen there. Acidic conditions are more, therefore it gives away oxygen. Temperature is normal. We are called as homothermal. Homothermal means same temperature will be maintained. Okay. Now let us come to the different habits. Suppose if the acidic condition is very high, what will be your condition? Will you be very active or lethargic? Lethargic means will you be very dull or will you be very active? You will become dull. What is the simple reason? Because in my body, if I am having more acidic conditions, hemoglobin will lose oxygen binding capacity. So hemoglobin will become less efficient. When I become less efficient, less burning of glucose will happen, less energy will come, I become very dull. This is one reason they say be very careful while having acidic diet. These days you might be hearing about alkaline water. Are you hearing it or not? Alkaline water is very good for health. Whatever water that we are drinking, it is acidic water. So you have to take alkaline water, your health will be good. You need not go for alkaline, simple water is also good only. But that is the importance. So your blood should not become acidic, your inside should not become acidic, therefore blood is called as a buffer. Blood is a buffer. Because once I take some acid in the sense maybe I'll take a lime or I take an apple, that will be having some acid. Immediately does it become acidic blood? No. It is buffer. And always that buffer will maintain a pH of 7.2 to 7.4. So within the 7.2 to 7.4 range, this is a buffer. Whatever acid diet that I take or whatever alkaline diet that I take, immediately blood does not become alkaline, blood does not become acidic. It will maintain a buffer. But beyond this, if you are still taking some acidic diet, then definitely the people will become lethargic, metabolic activities will drop. Why the metabolic activities are dropping is the simple reason, hemoglobin will lose oxygen binding capability. Okay. Just one common example I'll tell. These days I am seeing that many of my students where I teach, they will be eating heavy biryani, and with that biryani they want to digest it, therefore they will be drinking some Coke, Pepsi. Coke or Pepsi you are taking means you are giving more acidic diet. That will have phosphoric acid. Coca-Cola, Pepsi, they definitely add phosphoric acid to it. So pH will be very low. It is always under 7. Digestion does not happen properly. Maybe they will be belching, but belching does not ensure your digestion. So that will give you acidic diet, and slowly those people will become toxic, they become fat, and all sorts of problems will arise. Proper metabolic activities will also stop. Okay, so that is the importance of this respiration process. And always to be active, take a normal diet, not highly acidic, not highly alkaline diet. Okay, so this is about hemoglobin. Okay, now just 2 more minutes. This hemoglobin, as I told you, first of all it will act as a deoxy form. Deoxy form means oxygen is not present. So once oxygen comes, it will go and bind with the oxygen. We call it as oxy hemoglobin. Deoxy hemoglobin, oxy hemoglobin. Most important questions that appear is, what is the geometry with respect to deoxy as well as oxy? What is the magnetic momentum, or how many number of unpaired electrons are present? What is its electronic spectra or absorption spectra? How many peaks may appear? What is the color? These 3 questions will definitely come. With respect to geometry, they may ask you coordination number. What is the bonding mode of iron to dioxygen? What is the bond angle between iron and dioxygen? Is it 130 degree, 140 degree? What is the distance between the iron and the porphyrin nitrogen? What is the distance between the iron and the nitrogen of proximal histidine? All these things are very, very important. So whatever points that I give, note down each and every point. Okay? Write down. First one. First protein we are starting with, hemoglobin. Put the main heading as hemoglobin. It is an oxygen binding protein. It is an oxygen binding protein found in vertebrates. Found in vertebrates. Found in vertebrates. Hemoglobin is a tetramer. Tetramer means hemoglobin is not a single unit. Altogether there will be 4 units of it. Hemoglobin is a tetramer. That is, it has 4 subunits. Hemoglobin is a tetramer. It has 4 subunits. These are called alpha 2 beta 2 subunits. Alpha 2 beta 2 subunits. It means 2 alpha units, 2 beta units. What is the difference? What is the difference? I am drawing roughly, you need not draw it now. Suppose if this is porphyrin. Now every time I say porphyrin, you need not draw pyrrole rings, methane bridges, all those things. Simply show 1, 2, 3, 4 nitrogens, show these rings, that is enough. You have to imagine it as porphyrin. Iron is present in the center. With this iron, there is a 5th coordination site and a 6th coordination site. At 6th coordination site, either water molecule or oxygen will come and bind. At 5th coordination site, this will be bound with a proximal histidine. This is a protein. It is a protein part. Okay? So in this protein part, it will be having some amino acids. Protein is made up of amino acids. How many amino acids will be present? That depends. Hemoglobin altogether has 4 subunits. 2 are called as alpha. Alpha will have 141 amino acids, and beta will have 146 amino acids. Okay? So what is the difference between alpha and beta? It is the number of amino acid. It means, suppose if this is a protein chain which has 141 amino acids, that I call it as alpha, beta will have 146 amino acids, 5 more amino acids more than alpha. So if this is 1 unit, altogether alpha 2, beta 2, if this is 1 unit, I am just drawing it simply, try to understand. If this is iron and a porphyrin, this is 1. This is iron and porphyrin, a second subunit. This is a third subunit, and there will be a fourth subunit. Now here I am having a protein chain. Nitrogen, just I am drawing a simple ring, and to this nitrogen you have amino acids. How many? If it is alpha, 141. If it is beta, 146. So hemoglobin, we call it as a tetramer because it has 4 subunits. These 4 subunits, they are arranged approximately in a tetrahedral manner. They are approximately arranged in a tetrahedral manner. Tetrahedral manner means if this is inboard, these two will be out of board, almost. Okay? So they are not like in plane, they are almost arranged as a tetrahedral environment. One iron, second iron, just suppose this iron is bound with oxygen. First iron is bound with oxygen. Okay? Here also you have an iron. Immediately if this iron binds with its dioxygen, reversibility will be lost. Loss of reversibility. So these subunits are very close, and so close that if dioxygen binds, immediately it can bind to another iron, and this hemoglobin will die. No use of it. But how are we surviving? We are just surviving because of this globin chain, because of this part. What this part does is, this is an amino acid part. This will just like cover it. All this will be covering it. Protein. Okay? So this globin covers it in such a way that if this is dioxygen binding to one iron, this dioxygen will not interact with another iron. It is not possible because there is a globin chain within. So that globin or a protein part will protect the hemoglobin from irreversibility. There are separate reactions for globin. I'll give you those separate reactions, but this is what is protecting us. And whenever I say hemoglobin, what is hemoglobin actually? This is hemoglobin, not just this one. Whenever I say hemoglobin, it is 1, 2, 3, 4. Along with this globin chain, along with this histidine, above also there will be histidine. I draw it separately, but above there will be one more histidine. We call this histidine as distal histidine. This one as proximal. Okay, so what are the units that you have? Hemoglobin means altogether 4 subunits. 2 are called as alpha, 2 are called as beta. Alpha will have 141 amino acids, beta will have 146 amino acids. One iron cannot directly interact with another iron because there will be a globin chain in between. And along with this, iron surrounded by porphyrin, each iron is also attached to proximal histidine. Above there will be another histidine called as distal histidine, but there is no direct bonding with it. It is just close to that iron, there is no direct bonding, it is vacant. That vacant site will be occupied by dioxygen. Okay? Next. When this iron is not present, today you just understand most of the part. Can you see some space? There is some space. This space is anywhere around 80 picometer. The core or the hole or the space is around 80 picometer. Iron high spin and iron low spin, their sizes are lot different. This is 92 picometer. This is around 70 picometer, 70 or anywhere around 72 picometer. Okay, so what is the size of the porphyrin's core? It is 80. In this 80 picometer, can 92 picometer sit? It cannot sit. Space is only 80, but this is anywhere around 90 picometer. It cannot sit into the pore. Therefore, it will be outside the porphyrin plane. So that is the reason whenever we draw this porphyrin, we draw porphyrin like this. If this is the porphyrin, iron we draw it outside. Now it is attached to histidine. So iron is present outside. What is the reason for it? Deoxy, iron is present outside. The simplest reason is the size of the high spin iron is larger than the core size of the porphyrin. Therefore, it cannot fit into the hole, it will come outside. If this is iron, this is coming outside of the hole. But whenever dioxygen comes and binds, once dioxygen comes and binds, high spin iron will become low spin. Low spin iron size is around 70 picometer. So 70 picometer can easily sit into 80. So whichever iron that is present outside will suddenly go inside once it is taking dioxygen. Once it gives away dioxygen, again it will come out. Again it will get inside. That process is continuous. Okay? It is a continuous process. Today, for most of the time, you try to understand the concept. Points I'll slowly give. Just imagine if this is porphyrin. Okay? Inside is iron. Inside there is a space. In this space, iron cannot accommodate because iron is high spin, therefore it is coming out. So all that porphyrin is, it is like this. You can just imagine nitrogens. All that porphyrin is like this, nitrogen and iron is coming out. But once dioxygen comes and binds, that iron high spin will become low spin. Once it has become low spin, it will enter into the plane of the porphyrin. So once it is entering into the plane of the porphyrin, there is a movement. This iron is attached to some protein. Can you see? Inside it is attached to some protein. So once this iron is moving up, what is happening to this protein part? It is also moving. It is just like I am having a rope. You are holding that rope. I will pull the rope. Will you come along with the rope or not? So I am stimulating you through the rope. The same thing will also happen here. Once dioxygen comes and binds to one iron, this will be like a pulling effect. This pulling effect will go and stimulate second subunit. And once this gets stimulated, this will take dioxygen more fastly than the first unit. Usually what should happen to the rate? Stepwise, it will decrease. But in hemoglobin, I said it will increase. In reaction mechanism, if you could remember, I said it will increase. Why does it increase? Because once this is taking dioxygen, it will stimulate the next subunit and this will take dioxygen more easily. Third one, both will stimulate the third one will take still faster. Fourth one, all the three will stimulate, so this one will take much faster. For that reason, the rate or the stability constant will be increasing in a stepwise manner. What do you call that process as? There is a name for it. This mechanism where one is helping the another. Cooperativity. And one regular question comes, which mechanism explains cooperativity? Which mechanism explains cooperativity? Answer? Perut's mechanism or trigger action mechanism. Okay? Perut's mechanism or trigger action mechanism. Now first you write down a few points, then again I will explain this. We have to separately draw deoxy hemoglobin, oxy hemoglobin. You don't draw all these things. We have to draw it neatly again. This is just for your understanding only. Did you write 4 subunits? Alpha, beta. Alpha 141 amino acids. Beta 146. Okay. Next. The 4 subunits do not directly interact with one another. Because of globin chain. Because of globin chain. Next. For each subunit, the core of the porphyrin, core means the central portion, C-O-R-E, core. The core of the porphyrin has a size of 80 picometer. 80 picometer. Next. The size of high spin iron The size of high spin iron is around 90 picometer. The size of high spin iron is around 90 picometer, whereas low spin iron is around 70 picometer. Therefore, in deoxy hemoglobin, the iron will be out of the plane of porphyrin. The iron will be out of the plane of porphyrin. Out of the plane of porphyrin. Next, the coordination number of iron will change from 5 to 6. The coordination number of iron will change from 5 to 6. 5 to 6. First you draw these diagrams, then separately we will take up points. Lot of points will come for bioinorganic. You have to write down a lot. Deoxy is also called as desoxy. Deoxy or desoxy. I'll write it here. Deoxy hemoglobin or desoxy hemoglobin. This is oxy hemoglobin. This is distal histidine. This one is proximal histidine. Iron is present in the plane of porphyrin. In this case, iron is present outside the plane of porphyrin. The fifth coordination site is a nitrogen of imidazole of histidine. Sixth vacant coordination site will be occupied by your dioxygen. So this is your sixth vacant coordination site. That can be occupied by water molecule or it can be occupied by dioxygen. Same CH2 and protein, there also CH2 is present, but simply we denote it as a protein. What is the role of distal histidine? Do you have any role for it? Because in most of the literature, did you anywhere find distal histidine? Simply whenever we say deoxy hemoglobin, oxy hemoglobin, you draw these two diagrams only. You have never seen that. But there is a lot of importance for it. What is that importance? Any one of you can tell? What is the importance of that distal histidine? Very important role. Okay, what type of bonding is present between iron and dioxygen? Reversible or irreversible? Reversible. Reversible means this particular bonding is weak bond. It is not a strong bond. So it can break at any time. It may break at any time. There should be some stability for it. And how does it get stability? It gets stability from hydrogen bonding. It gets stability from hydrogen bonding. So oxy hemoglobin, do you find any hydrogen bonding? If that is the question, what is your answer? Yes, definitely yes. Where is the hydrogen bonding coming from? It is coming from the hydrogen of distal histidine. Okay, so that will offer some stability so that dioxygen can stay nicely there. That is the importance of a distal histidine. Whenever dioxygen is absent, that distal histidine is also present here. I just did not draw, but it will be like this. It is just like this. But whenever dioxygen comes, slowly this will move. It means whenever dioxygen is absent, it is not important. But whenever dioxygen comes, it is completely changing its conformation, and this will come, make a hydrogen bond that will offer some stability. So that is the important role of distal histidine. Okay? Finish diagram. Now just listen to the different aspects. First I'll explain, then for each and everything I'll give you the points. Three important aspects as I told you. First one, geometrical aspects they will be asking you, magnetic aspects, electronic aspects. First let us come for the geometrical aspect. First important question, what is the coordination number of iron? Here the coordination number I can call it as 5, that depends on the options. Out of this 5 coordination number, 4 are the nitrogens coming from the pyrols of porphyrin. 5th is also a nitrogen coming from a imidazole histidine. This is an imidazole of histidine. So altogether it is in nitrogen environment. All 5 donor atoms are nitrogens. 4 nitrogens are coming from pyrols of porphyrin. 1 nitrogen is coming from imidazole of histidine. There is a 6th vacant coordination site. If I don't consider the 6th vacant coordination site, the geometry we can call it as a square pyramid. But it is not a perfect square pyramid, it is a tetragonal square pyramid. You can call it as a tetragonal distorted. What is the reason? If this iron is present exactly in this plane, I may call it as a square pyramid. But it is not like this, it is coming out. Therefore we call it as a tetragonal distorted. So what is the geometry means? Tetragonally distorted square pyramid. That is one way to understand. Suppose in the option you do not have tetragonal distorted, you have octahedra, then that is your answer. Distorted octahedra. How did you get distorted octahedra? Because there is a vacant coordination site which is bound to a water molecule, solvent, water molecule. So what is the coordination number? 6. 5 are nitrogens, 1 is oxygen coming from water molecule of the solvent. Then I call it as an octahedra. It is not a perfect octahedra, distorted octahedra. Okay, so final point. What is the geometry of deoxy hemoglobin? Geometry is distorted square pyramid or distorted tetragonal or distorted octahedra. Any of these 3. Okay. Coming to the oxy hemoglobin, what is the geometry? It is called as a perfect octahedra. Okay, we call it as a perfect octahedra. So geometry, distorted octahedra or distorted square pyramid, perfect octahedra. Geometry is completed. Next point that they ask you is about magnetic property. In magnetic property, how many unpaired electrons are found here? What is the magnetic property of that? Can anyone? First you tell me the magnetic property. Based on that, we'll analyze the number of unpaired electrons. This one is paramagnetic. Okay, what will be the magnetic momentum? .8. It is found to be 5.45 Bohr magneton. Okay, remember this point. You expect anywhere around 4.9 because there will be 4 unpaired electrons, T2G4 Eg2. But how much paramagnetic momentum you are seeing? 5.45. It is higher. It means there is some orbital angular momentum also. It is very, very high. It is 5.45. Okay, this is paramagnetic. Next one, diamagnetic. How is it diamagnetic? Okay, what is the spin of iron? Iron plus 3 plus 2 plus 3 plus 2. So 2 answers I am getting. Plus 3 some are saying, plus 2 some are saying. But everyone is saying low spin. Low spin is fine. Some say iron 2, some say iron 3. Which is correct? Iron plus 2 low spin. Iron 3. Now let me conclude. It is iron 3 low spin. In most of the books it is given as iron 2 low spin. In some standard books also you can see iron 2 low spin. If I say iron 2 low spin, how many number of unpaired electrons are present? Iron 2 low spin? T2G6, Eg0, no unpaired electron. But dioxygen is coming and binding. In dioxygen you have 2 unpaired electrons. It is a triplet. So it has to be paramagnetic. Why is it diamagnetic? Did you get the point? If in hemoglobin iron you say that it is iron 2 low spin, no unpaired electron, but dioxygen is bound to it, dioxygen is a spin triplet state, it is having 2 unpaired electron, it should be paramagnetic, but it is diamagnetic. Then another explanation has come. What is that another explanation? Dioxygen can stay as a triplet, dioxygen can also stay as a singlet. It means 2 electrons which were same spin, they will be having opposite spins, it will become a spin singlet. So for becoming spin singlet it requires some energy. Triplet is stable, but for getting the diamagnetic nature it has to become singlet. It requires energy. Who is giving that energy? No explanation. System has to give, but why system will provide that much of energy? So there is no proper explanation for iron 2 low spin. If it is iron 3 low spin, then how many unpaired electrons? Iron 3 low spin is present. How many unpaired electrons must be there? Iron 3. T2G5. Now you have a problem. It is paramagnetic or diamagnetic? But you are saying diamagnetic. Okay. How is iron in deoxy? Iron 2. But oxy, we are saying iron 3. Where did that electron go? Oxygen has taken it. Oxygen is taking that extra electron. Once that oxygen is taking that extra electron, that will become superoxo. Oxygen will become superoxo. In that superoxo, whenever we have 2 unpaired electrons, now there is a third electron. Because it is taking 1 electron, it has become superoxo. There is 1 electron in oxygen, there is 1 electron in iron. Both will undergo antiferromagnetic coupling. It is called as antiferromagnetic coupling. Due to antiferromagnetic coupling, this will become diamagnetic. So though there are 2 unpaired electrons, it is still called as a diamagnetic center because of strong antiferromagnetic coupling. In that antiferromagnetic coupling, I may just show this electron to be downspin. So that one is upspin, another one is downspin. Any electron that I show could be up or down. Okay? So if one is behaving like up, the another will be behaving like a downspin. They almost like couple, and therefore it will show diamagnetism. Okay? So my proposal is iron 3, but dioxygen is superoxo. Okay? What you are saying is iron 2, but dioxygen is dioxygen only with a triplet state. Right? Now who will vote for me and who will vote for her? Because if you want to vote for me, I should show some evidence for you. I have to show some evidence. And I have a very strong evidence. That evidence is coming from stretching frequency of this dioxygen. It was found to be around 1050. I measured this stretching frequency. When I measured, I got a value of 1050 wave numbers. What is the meaning of it? When do you get 1050? Yesterday I have given you data. 1555, 1100 to 1150, 800 to 900. So 1050 is close to superoxo. Therefore, oxygen might be converting into superoxo. When does oxygen convert into superoxo? When iron 2 converts into iron 3. Is this evidence okay for you? That is one evidence. Second evidence, another strong evidence come from XPES. What do you mean by XPES? X-ray photoelectron spectroscopy. According to X-ray photoelectron spectroscopy, for iron the oxidation state was found to be anywhere close to 3.2. according to XPES. So I got an oxidation state for iron to be around 3.2. 3.2, is it close to 3 or is it close to 2? 3. It means iron must be present in plus 3. 1050 means oxygen must be present in a superoxo form. With these two evidences, now I can tell that iron is present in plus 3 low spin state with 1 unpaired electron. Oxygen is present as a superoxo with 1 unpaired electron. Both are very close, therefore strong antiferromagnetic coupling will occur. That will lead to diamagnetism. Therefore, oxy hemoglobin is diamagnetic. Okay? Deoxy hemoglobin para. 4.9 is not the magnetic momentum, 5.45. It is according to Pauli. And whereas that diamagnetism, though there are 2 unpaired electrons. So magnetic data is also completed. Okay? Just we have one more data, electronic data or absorption spectra. When I say absorption spectra, in exam they will ask you what is the color. Absorption spectra is related to color. What are the colors? These points I will give you, don't bother. Color. Deoxy hemoglobin is purple color. We call it as a purple. Oxy hemoglobin we call it as red color or purplish red color. The reason for the change in color, this is purple, red. Change in color. Okay. These data you have to remember. In absorption spectra, 2 bands will appear for deoxy hemoglobin. 2 bands will appear. Due to those 2 bands, you will be getting color. One band will appear at 555 nanometer. The another band will appear at 400 nanometer. 555 and 400. They are in the visible region only. Visible region is between 400 to 750. So these are falling within the visible region. Therefore, deoxy hemoglobin is bright colored, intensely colored. Second question they ask is, what is the reason for color? What is the reason for color? 2 peaks are appearing, but why are 2 peaks appearing? D to D transition? No, there is no D to D transition. There is no D to D transition. Pi to pi star, ILCT, intra-ligand charge transfer transition. We have heard about porphyrin, you have drawn many times. Plenty of conjugation is present, that is giving you the color. So that is called as pi to pi star intra-ligand charge transfer transitions. The reason for color is CT transitions. What type of CT? Intra-ligand, ILCT. ILCT, okay. Next, oxy hemoglobin. It is red colored, purplish red. The color change is because the absorption peaks are also changing. Previously I was getting one peak at 555, another peak at 400 nanometer. But now I am getting it at 451 and 476 nanometer. Both peaks are changing. Where is the change that you got? This is iron with porphyrin. This is iron, porphyrin and a dioxygen. Dioxygen has also come and bound. So due to the interference of iron dioxygen binding, you will be getting 2 different peaks, one at 451 and one at 476, and the color of oxy hemoglobin is due to these 2 peaks. Okay? So now let us just conclude. Geometry, deoxy and oxy, both let us compare. Geometry is distorted octahedra or distorted square pyramid or tetragonal square pyramid. Oxy, it is a perfect octahedra. Okay? Magnetic momentum, para, dia. Magnetic property, momentum 5.45, 0. It is diamagnetic due to antiferromagnetic coupling. Truly speaking, there are 2 unpaired electrons, but it is behaving like diamagnetism because of a strong antiferromagnetic coupling. Next, coming to the absorption spectra or the electronic spectra, 2 peaks appear for deoxy, one at 555 nanometer and the another one at 400. One is called as a Q band, another one is called as a SORAD band. The SORAD band is 10 times more intense than the Q band. Okay, intensity wise this is more intense, 10 times more intense. Now when I go to oxy hemoglobin, again you will be getting 2 peaks but at different wavelength. One is at 451, the another one is at 476 nanometer. So the color of deoxy or oxy is due to these two absorption peaks. Okay. Just write down a general data. All these points will take up in the next class. Stability, we have to also discuss the bonding mode of dioxygen. What is the angle? How did I draw this? Did you notice? I have drawn it like this. I did not draw it like this. If anyone has drawn like this, it is wrong. Because this is giving you 90 degree. But this angle will be 133 degree. Okay? In human beings, the angle will be 133. Depending upon the organism, it will change from 115 to 155 degree. But at least you remember 133 in human beings. Right? You just write down a general data today about iron. Species is iron. Spin. First let me take high spin, low spin, high spin, low spin. Configuration, this is D6, T2G4, EG2, D6, T2G6, EG0. D5, T2G3, EG2, D5, T2G5, EG0. Next, do you expect any distortions? T2G4 unsymmetric, distortions are present, no distortion, no distortion, distortion. All this is for octahedra. Okay, so very frequently you will be getting these configurations in biocoordination chemistry. Let it be hemoglobin, let it be myoglobin, let it be hemerythrin. You will be getting either iron 2, iron 3, high spin or low spin, electronic configuration, and which one will have some distortions in one table I have given you. Whatever points that I have discussed today, I will be giving the points tomorrow. In shortcut I will give. I will send you the PDF, the notes I am having with me. So I will just give shortcut points. Full notes I will just send it as a PDF. Tomorrow morning timings sir has told you? Okay, morning session sir will be taking. Afternoon after lunch from 2 I will be taking. Okay, I will be taking from 2, we'll see up to 4 or 3:30.